Je sais où aller, je suis resté près de toi, ma bien-aimée. Tu m'as redonné la foi, je suis resté, même si tu n'étais plus là. Je sais où aller, je sais où aller, je sais où aller.
Good morning, guys.
Good morning.
Good morning.
Okay, I hope we are all doing fine. We'll be starting in 2 minutes at 9:05. So, if your friends are not yet with us, please remind them to start because I'll start even if everyone is not here. Okay, so I'm guessing we can start our lesson today, despite the fact that we are only 10, unfortunately. But time is of the essence and it's imperative that we begin. I hope you guys had a good weekend and the week had begun well, the lesson so far. And I hope you went through the stuff we did last week. That was just a rappel, mathématique, vectoriel. Those are just some tools we are going to be using in mechanics. Today we will begin the real mechanics now, the stuff you will be working with. And the first topic is called cinématique du point matériel. In English, we call it kinematics. Okay, cinématique du point matériel. Now, in cinematic, we focus on the movements of objects. When we're talking about kinematics, what we are focusing or we are looking at the movements of objects, the movements of particles and all. So when we talk about cinématique du point matériel, we are talking about the movement of a point matériel, le mouvement d'un point matériel. Now, the most important thing to note, or not the most important things, but one of the most important things to note about cinematics is we do not take into consideration the factors or the things that are causing that movement, à savoir les forces. We do not look at forces here. What's primarily concerning us in cinematics is movement, the vitesse or velocity, the acceleration, the speed, and all that. That's what we focus on in cinematics, and we are just going to be limited to that. All that is movement without focusing on what's causing that movement. We are going to look at the cause of movements when we start doing chapter 2, if we're going to do it, inshallah, which is dynamic du point matériel. That's when we'll look at the causes, things like forces and Newton's laws of motion and all. One thing I forgot to mention last week is this polycopy I'm using is a GJM polycopy. Now I know not everyone here is coming to GJM or is going to do GJM. I know there's people going to ENSA, there's people going to ENSAM, there's people going to SVT, to the EST, and all that. But like I explained to you during the initiation session we had, the concept is always the same. And what I'm trying to give you here is the concept. Physics in Morocco will remain physics in the United States. The same physics in Algeria is the physics in Zambia. What's just different is the application. So perhaps the way we might apply it a GGM might be different from the way ENSA applies it. Perhaps ENSA does more application than EST. That's just what's going to be the difference. But if you get the concept, even the application is going to be easy. So don't go to your schools expecting to find the exact same things. The applications might be different, but the concept is always going to be the same. Un point matériel here that we're doing is going to be the same point matériel you'll be studying when you get to your faculties. So uh, I've heard people say, no, what we did in summer lessons was nothing, it's nothing compared to what we do at the ENSA and all that. That's not true, because if you focus on the concept you're being given, what you're going to do at the ENSA, even if it's not exactly the same as what we are doing here, you still have the concept, the v-test, the acceleration, how to use trigonometry, how to use calculus with all this, and things are going to make sense for you. So I emphasize, focus on the concept of what we are learning here. Try to understand exactly what we are doing, so that even if they give you a very complicated question to solve as application, you'll be able to do it. Yeah, so I guess that's that. That was just to buy some time as people are joining us. We're now at 19, so well and good. We can advance. Then we look at the notion d'un point matériel. I remember I explained this. On appelle point matériel tout corps solide dont on peut négliger les dimensions lorsqu'on décrit son mouvement. And that's what's most important about a point matériel, is that it's got dimensions that we can overlook, on peut les négliger. Okay, it's like they are so small compared to where the observer is. As I explained last time, it can be a small point, like maybe an electron and all, if we're going to look at it directly. And it can also mean an object that's very far away from us or from the observer. And since the object is very far away from us, its dimensions, its length, its breadth, its height, they become very small with respect to where we are observing it from. So those things, we can just leave them out in our calculations. And that's what we call un point matériel. So at the back of your mind, don't have the notion that un point matériel is just a point, since it's called point. So it's just a small point, a dot. No, it can be any object, but what matters is where the observer is this time. If the observer is so far away from the object that the dimensions of the object become so small, then we can study it under mécanique du point matériel. If not, if its dimensions are still significant with respect to where the observer is, then we are going to study it in mécanique des solides or something like that. So that's un point matériel. It's any body or any solid whose dimensions we can treat as very insignificant. You know, on peut le négliger. They are so small with respect to us, the observer. Yeah, that's that about un point matériel. Then we have espace référentiel et repère et temps. We can look at un référentiel. Referential. Whenever we are studying movement of something, we always study that movement with respect to something, okay? Par rapport à quelque chose. You cannot just study a movement in thin air. You won't know how it's moving, how far it's moved, and all that. So we use what we call a referential. In English, we call it a frame of reference. So the frame of reference is going to help us now study this movement of this object. It's going to help us take note of whatsoever change in positions. It's with respect to this that we study this movement. So now they are telling us here in the diapole that lorsque nous parlons de mouvement d'un point matériel, nous parlons de mouvement par rapport à quelque chose. Pour décrire ces mouvements, il nous faut donc dire par rapport à quoi ils ont lieu. Il nous faut choisir un référentiel. Ce référentiel sera en général défini par un solide, par un système concret dont on peut parler. Exemple, les laboratoires, le sol terrestre ou un endroit particulier, ou bien la Terre. Okay, so for example, you are studying the movement of a satellite. I like giving the movement of a satellite because at the end of your course, towards the end, you are going to look at satellites and all those things and the movements they make. So when you look at the movement of a satellite around the Earth, for you to be able to study exactly how that satellite is moving, the speed or the velocity at which it's moving, the displacement it makes in a certain period of time, you have to be studying it against another thing. You know, you have to have something that's going to help you take note of all those changes. So for example, you can use the Earth as your frame of reference to the movement of the satellite. So if, let's say, the satellite is at this position, you know, okay, it's next to the United States. Then the satellite moves and now it's next to China. So you know it would have moved that distance. The Earth there is just acting as a referential, a frame of reference. It's something we are referring to help us understand, to help us study, to help us take note of all the changes, of all the movements that this point matériel is making. I hope that's clear. And then we come to repère d'espace. Okay, a repère d'espace. So when we pick a referentiel, when we pick this frame of reference, normally we associate it to un repère. Okay, un repère. I talked about repairs last week. Un repère is simply a system of coordinates, like the way you used to study x or y plane or x or y z plane. Now this time around we'll go beyond the Cartesian plane, because that x or y plane is just the Cartesian plane. This time around we'll look at repère cylindric, repère spheric, depending on the movements of that point material. We are going to see exactly when to use coordinate cylindric, exactly when to use the coordinate spheric, or when we shall remain in the Cartesian. But that's just a repère d'espace. A repère d'espace is simply a system of coordinates in a space. We put it in a space and it helps us take note of the movements. Like when we looked at vectors last week, normally we were, the notation we were using for vectors, we had, for example, a vector U égale 2i plus 3j plus 4k. So we have that system of coordinates there, the EJK or the XYZ, helping us take note of exactly where the vector is. That 2i, 3j, and 4k is showing us exactly where the vector is in space. And that's what a repère does. Un repère est un système de coordonnées. Il sert à décrire le mouvement. Il a un rôle mathématique. Ainsi, à un référentiel donné, on peut associer différents repères. Les repères les plus utilisés sont dans l'ordre le repère cartésien, le repère cylindrique, qui dans le plan devient le repère polaire. I'll explain to you this point later on. Le repère polaire. And finally, we have le repère sphérique. Oh, sorry, not finally, but now finally, et le repère freiné. And then we have notation here. When we choose a referentiel and we associate a repère to it, and that repère has origin 0 and its base is EJK. We looked at la notion de base la semaine prochaine. J'espère qu'on a tous révisé. We all revised. So when we choose a referentiel and then we associate it a repère or a system of coordinates which has origin equal to 0 and has a base EJK, we note it as R, representing the referentiel, R, capital R from referentiel, and then between parentheses we have O, which is telling us that O is the origin, and we have EJK. It's not always going to be R O E J K. You just have to know that the R outside here is telling us that this is the referentiel we are using. Then the O is telling us that this is the origin. Then the three components that follow is telling us that these are the base of the repère we are using. Sometimes they can put P for the referentiel, c'est soit un référentiel P, the origin M, so we'll have P, and then we have between parentheses M, and maybe the bars will be using E, EFI, EK. That's just notation. So don't memorize it as R, O, I, J, K. No, it's not always the case. They have their significance or what they are telling us here. So R is a referentiel. Soit un référentiel R, we note it as R outside the parentheses. And then in the parentheses, we are now talking about the repère. What's the origin? So the origin is O. And what's the base of its coordinates? we have I, J, K, and that's how we note it. Then we come to temps. Le temps est représenté par un espace affin réel de dimension A, orienté du passé vers l'avenir, muni d'une unité de durée, la seconde. This is just French, it's fancy French, but it's still the same notion of time that we know. Time in seconds, you start counting from 1 second to 60 seconds, you get a minute. 1 minute to 60 minutes, you get an hour. Just that time there. C'est la notion du temps. And when we'll be looking at time, it's still going to be the same time that you are used to. Le temps de la mécanique classique est indépendant de l'observateur, soit le référentiel dans lequel on se trouve. Le temps sera le même. Okay, time is not going to change when you move from one referential. Maybe your referential is a laboratory, you're studying movements of things with respect to the laboratory you're in, or you are using the earth this time as your referential. Time is still going to be the same. Time is constant. Time is the same. It's independent of the observer or of the conditions that you are studying in, or that you find yourself or yourselves rather in. Are there any questions up to this point? Okay, good. Silence is taken as a no. Now we are going to look at movement. Again, it's just the same stuff you know, the same movement, you know, the displacement from one point to another, or maybe just moving from one place to another. Yes, that's the movement we are discussing. So here we have la notion de mouvement est inséparable de celle de référentiel. Il est impossible de définir un mouvement sans préciser le référentiel auquel il est rapporté. On dit qu'un point matériel est en mouvement par rapport à un référentiel si l'une au moins de ces coordonnées spatiales dans ce référentiel est fonction du temps. Les équations x égale fonction de temps, y égale fonction de temps et z égale fonction de temps sont les équations horaires du mouvement du point matériel sur la trajectoire. For you to take note of the movements of your point or an object, okay, if you're using coordinate system, at least the coordinate system has to be in function of time, because you have to take note of time changing as the movement or as the movement is being made, so that you can study things like velocity and acceleration. You cannot determine the velocity and the acceleration without knowing how the object was moving in time or with respect to time. So for us to be able to study the movement, for us to be able to study it accurately and to study it properly, the coordinates we are using, they should be at least en fonction du temps. We have to be able to take note of the time changing as we study the movements of these objects or these points. Then we come to a trajectoire. I'm sure it's a word that's new to many of you. Trajectoire is simply the path an object makes as it moves. Okay, so if you move from Cité to Manal, for example, and you just go down that road from Cité to Manal, that's going to be your trajectoire. That's the trajectory you would have taken to move from Cité to Manal. If you want, you can go around some other route and make a semicircle, or you can make a curve. But what's important here is that the trajectory is just the path some point or some object or a human being takes as they move from one point to another. That's a trajectory, and we can make equations from those paths that they make. Those equations we used to have, like y is equal to x squared plus x plus 1. Yeah, those are all just equations of the trajectoire, you know, of the trajectory, because the point is moving a certain path and it forms a curve. So we calculate the equation of that curve, and that's the trajectory of that point. So even here in mechanics, we'll be having some equations, we'll be forming some equations of the trajectory that a point makes as it moves from one point to another. But for now, what's worth noting Ce que vous devez retenir, c'est que the trajectoire is simply the path a point takes as it moves from one point to another. And this is still introduction. We're just defining some notions we'll be meeting de temps en temps as we shall advance in our mechanics. Now we come to system de coordonnées. Our stuff is going to get interesting a bit. We're no longer going to be just reading notes and all. L'étude du mouvement d'un point matériel nécessite un repère d'espace par rapport auquel la position de cette particule sera à chaque instant définie. Exactly what we're just from talking about. A repère is going to help you describe the movements. It's going to help you take note of the position of the point. It's going to help you define exactly where a point is located in space. Selon le problème à traiter, il convient de choisir le coordonnées ou le système de coordonnées le mieux adapté, celui qui facilitera le calcul. Okay, so we have several systems de coordonnées, several coordinate systems. What we have to do now as a mechanics is that we have to identify which coordinate system we are going to work with. You first look at the movement of your point, and then you choose which coordinate system is going to be convenient, which is going to be the best to work with. But don't worry, in Mécanique du point, you are not the ones who are going to be choosing these coordinate systems. They will be already chosen for you, and you just have to treat or to answer the questions that are going to follow from there. Okay, but you just have to note as engineers that you, when studying the movement of a point or of an object, the repère that you're going to use, the coordinate system that you're going to use, it has to be well adapted to the movement of that object. You cannot be studying things like rotation, things like rotation, and use the Cartesian plane. The Cartesian plane does not take note of rotations of objects. You have to pick a coordinate system that takes note of rotations, that's got some angles in it to help you study rotations as well, as we shall see as we advance. So we begin here with a coordinate Cartesian.
Sorry to take you back. Before movement, that was temps. Mentioned something like time is constant when an observer makes a reference to when an observer making a reference against something.
Okay, what I mean by time is constant is not that the time will not be changing as the object is moving, but what we mean is that it will be the same time we'll be studying in this in one referential as in another. So if let's say I'm studying in a laboratory, I'll be using the 1 second, 2 seconds, 3 seconds, 4 seconds, just like that. And if I use the Earth this time as my referential, I'll still be using the same time, 1 second, 2 seconds, 3 seconds, 4 seconds. It's not going to change. Le temps sera la même because time is independent of the observer. Yeah, that's what I meant to say.
Thank you.
All right, you're welcome. So we have the coordinate Cartesian here. So the coordinate Cartesian has as its base IJK. Whenever you'll be studying coordinate Cartesian, mostly you'll be working with IJK as the base du référentiel R, O, X, Y, Z. Base à référentiel R de origin O with the coordinates X, Y, Z. Then we have a figure here. It's not so clear, sorry, but it's just showing us how the Cartesian coordinate system is going to appear, but we have the x-axis, the y-axis, the z-axis, and then we have our vector there, OM, which is moving in space, and its position can be gotten from here. We have x, then we have y there, and we have z there, and you get your position. So if you're going to note it, your note OM is equal to XE is going to move XE plus YG plus ZK in space. On appelle vector position, this one the OM, as they have noted it here. OM is equal to XE plus YG plus ZK. Or you can note it in this way. You just write OM and have a column vector here, X, Y, Z. We know the first line or the first row is for the E, second is the G, third is the K. So no need to put X, E, Y, G, Z, K. When we use column vectors like this, we know already that the first row is E, second row is G, and the last row is the K. But if you're going to note it this way, in this equation form, you say OM is equal to XE plus YG plus ZK. But for the coordinate Cartesian, it's not so interesting. First of all, its axes are fixed. Yeah, when we start deriving or when we start calculating the velocities, you understand plus profondément or more deeply what we mean by its coordinates or its axes are fixed. But it's not so interesting. It's simple. It's just like this. OM is equal to XE, YG, ZK. That's pretty much all you need to know for now on the coordinate Cartesian. Where it gets interesting is when we start doing the coordinate cylindric. So coordinate Cartesian is mostly based on translations. I'm sure you guys know what a translation is. You just move from one point to another. I don't know if I can say in a straight line, but you are just moving from one point to another. You are not rotating, you are not revolving. It's just a movement from one point to another. That's a translation. But when we come to coordinate cylindric and coordinate spheric, they have translations and rotations. That's why they are interesting, or that's why they require a lot more attention or a lot more work, because you have both rotations and translations. That's why we have, you'll be noticing we have angles and all because of the rotations. So what they're telling us, the first statement is that ce système de coordonnées est très bien adapté à l'étude de mouvements ayant un axe de symétrie. So when they tell you that the movement that point is making has an axe de symmetry, I'm sure you know what an axe is. Axis. So we have z-axis, x-axis, and y-axis. So in coordinate cylindric, the way the point materiel moves is that it has an axe de symmetry. It means its movement is around a certain axis, such that the axis is cutting its movement in the middle. I'm sure we know what an axe de symmetry is. When we say line of symmetry, if an object has one line of symmetry, it means it has one line that cuts it in two equal parts. Yeah. So when we say an axe de symmetry, it means the shape that that object is going to form as it makes its movement, that axe de symmetry is going to cut it in two equal parts, into half. So as I said, in coordinate cylindric, we have translation and we have rotation. So it's going to be translating vertically down the z-axis. Okay, it's going to make this straight up and down movement down the z-axis. And then in the horizontal plane, the x or y plane, it's going to be rotating around the origin O. So it's going to be moving in a circle, some sort of a circle. But as it is moving in a circle, it's going up and down, up and down, up and down, in a circle, up and down. So you find that the form it makes is a cylinder, because it's moving up, down, so it's forming a height, and then it's also moving round like that at the same time. So it forms some sort of a cylinder, and that's why we call it coordinate cylindric, because the shape or the form that is formed afterwards is some sort of a cylinder, or not even some sort of, it is a cylinder. And as I mentioned when we just began our course, is that in mechanics, you have to be very, very imaginative. Try to picture things as we are explaining, as you are reading, as you are studying. Try to picture these things. Try to imagine them. You understand them better. So try picturing a point moving in a circle, but as it is moving in a circle, it's also moving up and down, up and down, up and down. You see that the shape it's going to form is a cylinder. And that's why we call this the cylindric coordinate system, because when the point is moving, it's moving in form of a cylinder. You know, the shape it's making is a cylinder. It's going round in the horizontal plane, and then it's going up and down in the vertical axis or the vertical plane. So when we come to this other figure here, that details the movements more, and the bars and how we're going to study the movement. We have our point here, M. M is what's making the movement, okay? So here at M, it's going around this axis, the Z axis is going around it like that. And as it is going around it, it's going up and down the Z axis, up and down the Z axis, as I have already mentioned. But for us to study the rotation properly, we are not going to study it from up here. We are going to project it downwards here at M prime. Okay, at M prime, we are going to project it downwards here so that we can study it properly down here in the horizontal plane. Then we have rho there. Rho is simply to show us the distance that M is from the origin in the horizontal plane. This rho here, just showing, because M is up here. The point we are studying is M. That's what we are interested in. But to simplify our movements, we are going to break down this point M by doing some projections. So the first projection we're going to make is this M prime here, and M prime is going to show us the movement of M in the horizontal axis, how M is moving in the horizontal axis, the X or Y plane. Not the horizontal axis, sorry, but the horizontal plane. I excuse myself there. It's the horizontal plane, the X or Y plane. This is the horizontal plane. So how is this M moving in the horizontal plane? We have this rho to help us. Then we have the angle phi. The angle phi is going to show you the rotation of this M around the center, or around the axis of symmetry, the symmetric axis, we can call it Z. The angle it's making around that is phi. So as it is rotating round, there it's rotating round, the angle phi is going to be changing, maybe from 70 degrees, 80 degrees, 110 degrees, 360 degrees, 720 degrees, just like that. It's going to be rotating. So this phi is going to be telling us how much it's rotated, the angle it's made around this axis of symmetry, the Z axis. So that's your angle phi. And then we have the base vectors. The base vectors in the coordinates, in the cylindric coordinate system, we have rho, phi, and k. But the k, you can just use k, because the Z is the same Z in the Cartesian plane. So you can just use k. Rho, phi, k. These are the base vectors. So rho is in the same direction as rho down here. That's why we call it rho. It's in the same direction as rho. It's like continuing from the origin there in this direction rho is in. That's rho. Then we have phi. According to the rule of base vectors, is they are supposed to be orthogonal. So phi is going to be perpendicular to rho, and these are going to be the horizontal vectors in this case, in this bars, rho and phi. Then we'll have k being perpendicular to both these two, because all three vectors are supposed to be perpendicular to each other, which is going to be projected in the vertical plane. So these two are going to be perpendicular to each other in the horizontal plane. Then the third one is going to be perpendicular to them in the vertical plane, so that they are all properly perpendicular to each other. And we can study the movement of a point in 3 dimensions, because both the horizontal and the vertical planes are put into consideration. So we have our point there, M, and its movements. So we can look at vector position. Okay, not yet. So we can say M est repéré par rho, phi et z. So when they tell you M est repéré par rho, phi, z, what they mean is it is these 3 niggas here that are going to help us define exactly the position of a vector or of a point in this coordinate system. It's these that are going to help us study its movement, rho, phi, and z. Rho being the distance there I told you about, phi being the angle it's making as it rotates around the axis of symmetry, which is z, and z being the axis of symmetry here, as I told you, it's going to be translating translating up and down this Z axis. So even the Z is going to help us define exactly the position and the movement. Changu, you have your hand raised. You can speak.
Yes, I wanted you to just kindly repeat on the thing you're saying for perpendicular for Ika, Phi, and the like. I didn't get it clearly.
Okay. When we have a base, normally a base is supposed to be, we say it's orthonormé, okay? That's what we looked at last week. We said une base orthonormée. So the base orthonormée, it means its vectors are unitaire. Normé means they are unitaire, they are equal to 1. Then we also have the orthogonal part. The orthogonal is telling us that they are at 90 degrees to each other. So if you have a base and they tell you this base is orthogonal, it means all its vectors or all its base vectors are perpendicular to each other. So we have this also, the heureux, Phi, and Ek. They are orthogonal. That means they are all perpendicular to each other. So we have this heureux, it is perpendicular. Café crème. Oui, café crème. We have this heureux is perpendicular to Phi, and they are in the horizontal plane because we want to study the movement of a point in a three-dimensional space. So in a three-dimensional space, you look at both the horizontal planes and the vertical planes because you are taking into consideration the entire space, okay, the entire space. So you have to have vertical and horizontal axes or planes. So we have heureux and Phi in the horizontal plane, and we are going to have Ek or just K in the vertical plane, and they are all going to be perpendicular to each other. So it's like you have two pens that you put on a table, and they are at 90 degrees to each other. Then you put another pen, just where they are meeting at the origin there, you put another pen, but this time it's standing, and you form those three axes, and you have all three of them at 90 degrees to each other, because that pen that's standing is going to be at 90 degrees to the one pen on the left, and it's also going to be at 90 degrees to the other pen on the right. And that other pen that's on the right is going to be both at 90 degrees to what's on its right and what's standing just next to it. Same thing for the other one on the right. And that's how we know that they are orthogonal. They are at 90 degrees to each other. It might not be clear in the figure here, but as I told you, you guys need to be imaginative. You need to imagine. So just picture these as being 90 degrees to each other, and these two as being in the horizontal plane or just lying down on the table, and Ek as being vertical, standing, it's facing up as the vertical axis, Ek. I don't know if that's clear.
It's very clear. Thank you.
Okay, yeah, welcome.
I've got also a question.
Yes, please.
Can you say that Phi is also perpendicular to the y-axis?
It's perpendicular to the y-axis. No, because that's a different coordinate system now. The y-axis, the x-axis, and the z-axis belong to the Cartesian coordinate system. Now here we are in the cylindric system. The only thing that's being carried over from the Cartesian system to the cylindric coordinate system is the K. So only the K has the right to claim that it is perpendicular to heureux and Ek. X and Y, they might not be perpendicular to the Phi and the heureux because they are not in the same coordinate system. They are not in the same bars, so they are not necessarily orthogonal to each other. They might be, they might be not. It all just depends on how they are drawn, but they do not have to be at 90 degrees because they do not belong to the same bars. C'est clear?
It's clear.
Okay, awesome. Any other questions so far? Okay, no questions. I like that you guys are asking questions because when people are asking questions, it means they are following what's happening. So keep up with the same spirit. Don't be left behind. There are certain things that I might explain to you guys here that won't be explained to you when you go to school. I'm sure it's the same for other schools, but especially for you guys going to GGM, the woman has the habit of reading the polycopy. So all these things here, she won't be explaining to them. She's just going to read them and pass. So take advantage of this moment to try and understand everything. So when you go back, when you go to your schools, you won't have to start coming back, trying to understand there. When you get to school, you just advance and you'll give yourself at least an advantage over everyone else. So as I was saying, M est repéré par Rho, Phi, et Z. It means it is these three guys here that are helping us to define the position and the movements of the point M in this coordinate system. And then they tell us that M' est la projection perpendiculaire de M dans le plan OXY. As I told you, M here, we want to study the rotation the M is making. But for us to study it properly, we project this down there, so that we can isolate it a bit and we can study its rotation properly from the origin there and in this horizontal plane. Then they tell us H or H est sa projection parallèle à ce plan suivant l'axe OZ. So this point H there is a projection of M in the vertical axis. As we are studying M, you know, as I told you, M is being translated up and down this Z axis, okay? We can study it from here if we want, but for precision, we can translate it there and take note of exactly how it's moving on this Z axis, because the Z axis is what's helping us take note of these translations up and down, so we can project this point M all the way up to the Z axis on the Z axis, and we can study it with precision and accuracy. As I told you last week, when you get a vector parallel to another vector, they are the same vector as long as the direction doesn't change. They are the same vectors. Parallel vectors are equal. So if we project this point OM there, it's going to be the same thing because these 2 points, they are parallel to each other. This vector there and the vector there are parallel to each other. This rho, if I got this rho and I projected it up here, I got this one. They are the same thing. That's why rho, this time around, it's not is being shown as up there. But when you start studying it, you'll be studying it as down here, as you see. You'll be studying it as though it were down here. The reason why we are studying it as down here is because they are just vectors. They are parallel vectors. They are the same thing. So if I project this down there without changing its direction, it's going to be the same thing. So we have rho is equal to OM prime. So as I told you, it's telling us the distance from the origin to that point there, M prime, this rho. It's going to tell us that. So rho is equal to OM prime, its magnitude. So it's telling you that rho itself is not a vector. Rho itself is not a vector, it's a scalar. It's just telling you the distance from the origin O to this point M prime, which is a projection of M. So it's like it's the distance from this point to that point. It's rho. It's not a vector. Take care. It's not a vector, and it's positive and non-zero, greater than or equal to 0. Then we have phi. As I explained to you, phi is the angle that's helping us take note of the rotation this point M is making around the axis of symmetry, the Z, this phi here. So phi is the angle between OX and OM. So we take OX as our point de départ for the rotation. This is where we start from. This is like our 0. And then it rotates. When it rotates round and it finds itself here at OX again, it has made a 360 turn. Yeah. So when it rotates from OX to OY, it makes a 90 degrees, just like that, until it comes back there. But OX is simply our point de départ. That's why they're telling us that phi is the angle between OX and OM. So starting from our starting point here up to OM prime there, what angle has it made? Oh, it's made 270 degrees. Then you know that, okay, so my point M has rotated 270 degrees. Like I told you, a satellite rotating around the Earth, we can say we'll begin from Zambia, the coordinates of Zambia, where Zambia is, recording its rotation, the rotation of the satellite. Then the satellite moves from where Zambia is all the way up to where Australia is. And we suppose that the angle between those two is like maybe 180 degrees. Okay, no, not 180 degrees, 80 degrees, for example. So we take it as 80 degrees. We know that the satellite has moved 80 degrees around the Earth, because we are using the Earth there as our frame of reference. So we know it has moved 80 degrees. That's the rotation it's made. So it's the same for this point material also. It's making a rotation around this z-axis, lacks the symmetry, and this phi is simply going to tell us just how much it has rotated. It's going to help us take note of the rotations it makes, or the angles it makes. And then z, as I told you, M is going to be translating up and down the z-axis. Up and down the z-axis is going to be making that movement. So Z is going to be telling us how much the point M has moved up the vertical axis or down the same vertical axis. That's why they're telling us Z real quelconque. Real numbers involve both positive and negative numbers, and decimal numbers included too. So it can be negative when it starts going down the z-axis. So from 0 here, we know we haven't drawn the negative axis, but just imagine there's a negative axis there. From 0 here, if this vector starts going down this side, that's a negative movement, because the positive is going up, the negative is going to be going down. So Z can be positive, it can be negative. C'est une réelle quelconque, any real number. Is that clear up to this point before we look at the base locale, the coordinate cylindrique?
Yes.
Okay, lovely. Then we look at the base. For the Cartesian plane, we said the base is EGK. And I told you that that's not always going to be the base. Okay, the base is going to change depending on the coordinate system we have. So in the Cartesian coordinate system, we had EGK as the base. In the coordinate system cylindric, or the cylindric coordinate system, we are going to have ER, EFI, and EK or EZ or K, simply just K. It's the same thing. So if we note it as K, or we note it as EK, or we note it as EZ, it's the same vertical axis we're looking at there. So we have ER is this one here, in this direction there, parallel to rho. That's why we call it E rho. So E rho est un vecteur unitaire perpendiculaire au cylindre d'axe OZ, passant par M, indiquant la direction de rho croissante. This part here, indiquant la direction de rho croissante. E rho is in the direction of rho. So E rho tells us in which direction rho is, and they're telling us that E rho is perpendicular to this axe, the EK is perpendicular to it there. As I told you, these base vectors are all orthogonal. They are at 90 degrees to each other. Then we have EZ est un vecteur unitaire porté par OZ. So this axis there, OZ, this vector. The vector unitaire there is going to be EZ or Z, or EK, or just K there. We looked at this in the coordinate Cartesian. So on this axis, the unit vector, the just one unit there, is going to be our EZ, ou bien our EK, ou bien our K, just K. Then finally, we have EFI. EFI est un vecteur unitaire normal au plan défini par ERE et EZ, tel que ERE, EFI et EZ forment antièdre direct. So we know that these base vectors are supposed to be perpendicular to each other. So the EFI is not properly defined. It's a bit hard to imagine on this plane, okay? Because we know that EK is just simply this one going up, and we know that ERE is this vector there in the direction of rho. But where's EFI? Where is it? Because this is a three-dimensional thing. So for you to project it properly, it's a bit tricky. But one thing you must know is, since they are all orthogonal, they are perpendicular to each other. So EFI is just going to be the vector that's perpendicular to ERE and EK au même temps, at the same time perpendicular to these two vectors. Sorry, give me a second. So when we say normal or plan can also mean perpendicular to that plane. So we have a plane formed by Heureux and EZ. This is the plane. Ça, c'est le plan formé par Heureux et EZ. This one here, or this one here if you want, if you may, this and that, this and that, this and that. Ça, c'est le plan formé par Heureux and EK. So when we say EFI est normal, it is normal to this plane. It means it is perpendicular to this plane, making it perpendicular to both Heureux and EK at the same time. Is that clear?
You can just try to explain again.
Okay. So what they're telling us is that Heureux is this vector here, this base vector here, that shows us a direction of a rho there. So it's got this direction or orientation. Heureux is there. And then EK is c'est le vecteur unitaire porté par l'axe OZ, like in the Cartesian plane. So this OZ, the vector unitaire for this OZ is going to be EK. So it's going to be in that direction. So now you get to axes. When you get to axes, you put them together, you connect them at the origin, they form a plane. So these two, EK and Euro, they form ce plan. They form this plane there. Now, we know that from the definition of base vectors, they are supposed to be unitaire and they're also supposed to be orthogonal to each other. So, EFI is going to be perpendicular at the same time to EK and Euro. So, it's going to be normal. It's going to be normal to this plan or to this plane formed by OZ and Rho. We can just use Rho instead of saying Euro, because Euro and Rho are in the same direction. They are on the same line, we can say. So EFI is going to be normal. In other words, it's going to be perpendicular at the same time to OZ and Rho. It's like imagine it from here. You've got X and you've got Y on this figure here where the cylinder is. You've got X and you've got Y. And these two are perpendicular to each other. So we can say Z est normal au plan formed or formé par X et Y. Z is normal, or it's the normal to this plane formed by X and Y. That means Z is perpendicular to this plane there. And if it's perpendicular to this plane, it means it's perpendicular to both X and Z. So that's that about EFI. EFI is just perpendicular to both EK and Euro. So on the figure, we can clearly show the direction or the orientation of EK and Euro, but it's going to be a bit difficult to show the orientation of EFI. So we just imagine it. We imagine it first before we show it on the figure. We imagine it as being perpendicular at the same time to Euro and EK or K. Just give me a minute, guys. I need to set up my charger. My PC has a problem. Just one. Yeah, you guys can use it as an opportunity to drink some water, refresh your minds. Just 1 minute. Can you guys hear me?
Yes.
Okay. I'm very sorry about that. My battery died and my charger was not working, so I had to go back home to get another one because I'm doing this class from a cafe. But when I came back here, I found that it's not the charger that wasn't working, it was actually the sockets. So I had to start looking for sockets that are working in the cafe. That's why it's taking so much time. But I guess we are good to go now. We can continue.
I have a question before we continue.
Okay, you can ask.
Yes, yes. With an arrow, can you make a simple drawing for hero on M down there? Yes, yes. Here
What?
on M, like the way you did on M, which is on top there. You came up with EK, hero, Ifi.
Ah,
Yes.
how does this work? Just give me a second. Let me change the card. I don't know if you can see that. Can you see that?
Yes, yes.
That was your question, huh?
Yes, yes.
Yeah. So just parallel to this one here, just parallel to it, down here.
Okay, thanks.
Yeah, it's in the direction of ro. This ro, where ro is pointing, that's where euro is oriented. Or it's the other way around actually. Ro is oriented in the direction of euro.
Then the other one.
Okay. Uh, the car is going to be here. That's the car. Okay, or the car. Just parallel to this. It's going to be there. And then the earthy is supposed to be perpendicular to both these two. So it's going to be somewhere there, I guess, something like that. Just like the way it is there, you can just bring this down here.
Thanks. It's clear.
Okay, you're welcome. So here they are saying Eure, Efi, and Ez, they form un trièdre direct. So what does trièdre direct mean? Is there something down here I can use? No. Okay. This part again, I'll explain to you when we find it. It's somewhere ahead in the coup. So for now, we can just leave it as that. You guys can just know that they are direct. I'll explain what direct is. Ne vous inquiétez pas. And then Eure, Efi, Ez est la base cylindrique direct. local, where Ez is equal to K. As I told you, K in the Cartesian plane and in the cylindric plane, it's the same K. It's the same K you use. X and Y, we don't choose them in the cylindric, but the K, we use it also in the Cartesian and in the cylindric coordinate systems. So as we said, Ez is equal to K. So instead of writing Ez there, you can just write K so that you do not confuse yourself. Now, the vector position in the coordinate cylindric, when you're trying to take note of the position of a vector in the cylindric coordinate system, how do you do it? So the position of the vector, usually we start from the horizontal plane. We start from down here. The movements it's made in the horizontal plane. That's why we projected this M prime down here. From M, we projected the M prime. It was for it to help us study its position or its movement in the horizontal plane. So we usually begin in the horizontal plane, then we go up the vertical plane to exactly where the point is. So M, if you look at M, M is there. It's like this. This is the vector M or the point M. It's somewhere here. But question is, how did you move from this point O, the origin or the zero, to the point M? How did you move? Well, obviously, we moved like that, directly, there and there. But this is vague. It's not telling us anything. We moved from this point to this point. How are we going to know exactly the coordinates or where it is? You can see it, but what if I explain to someone who's not seeing what you are telling them? How are they going to know, or how are they going to imagine exactly where it is? So we need something that's more explicative, something that's going to show us, or something that's going to help us imagine exactly where it is. So instead of just moving directly from there to there, we are going to move like this. So from O, we are going to move to OM prime, like this. From O, we move to OM prime, following Rho. Then we will go up now, up until we reach the point M. So it's shown us exactly how we've moved. We've moved from O to OM prime. Then from M prime, we've moved to M, which tells us that OM is equal to OM prime plus M prime M, because we are moving like that. From there to there, we are moving from here to here, and from there to there. That's what they are telling us here. They are saying OM is equal to OM prime plus M prime M. Now,
Mr. Charles,
yes?
can you just, okay, on the same one there. So can you use the other way around as in trying to define the direction?
You want to go up and then like that? Yes. Yes, it's the same thing. It's the same because they are parallel lines. As we said, parallel lines are the same. It won't change. It's just going to change the order.
All right, thank you.
Yeah, you're welcome. Okay, so we've established that. Okay, no more drawings. We've established that we are moving from OM, so we are moving from O to M prime and from M prime to M. Or as our brother Mr. Salosa noticed, we can say from O to H and from H to M. It's just the same thing. You're moving from there to there, or you can move from there to there. But I have put these drawings. It's good Ruben asked, because we're going to need them. So this direction, just parallel to that, is euro. So this one is showing us euro, the direction of rho. It's oriented in the same direction as euro. And then up there in this vertical plane is K or EZ, like that. So since we're moving from there to there and from there to there, now we can take note of the coordinates or how exactly the object is moving in space. So we said OM is equal to OM prime plus MM prime. Now, OM prime is equal to what? OM prime is equal to rho, as we saw from here. Rho simply shows you the distance OM prime, the size of OM prime from there to there. It's a rho. So from the vector OM prime, this one, the vector OM prime, is going to be equal to rho, its magnitude, suivant E rho. E rho is giving us a direction. So whenever you have a vector, you have, as we said, the vector, we have its norm or its magnitude, then we have its direction, its sense, and all that. So the rho is going to give us its magnitude, and then the E rho is going to give us its direction because it's a vector. OM that we're studying there is a vector. So even as we are writing its coordinates, we are going to write them in vector form. So we'll have OM. OM is a rho suivant or following E rho. And then we will have this distance now, this distance here. This distance will be denoted with a Z because it's the Z axis there, the Z. We have just projected it there, the parallel line. So this is Z. So from M prime to M, it's just a Z coordinate, but we don't know exactly its size or its magnitude. So we just note it as Z, but it can be any number. But for now, we'll just take it as Z. So we'll note it as Z following K. So in the end, OM, which is equal to OM prime plus M prime M, is going to be equal to rho suivant E rho plus Z suivant K. Z being the size of this distance here from M prime to M, and K being its direction. It's showing you the direction because K, c'est un vecteur unitaire, mais ça nous montre aussi la direction de cette ligne plutôt. And then we have a rho being the magnitude of this line from 0 to M prime, and E rho showing us its direction. Okay, nice. So when we come down here, let me just clear these things.
I've got a question before you proceed.
Okay.
When you projected the vectors at point M prime, why didn't you include the if?
If you are not using it for now, because it hasn't intervened in our notations for now, because we don't need it. What we are interested in is, we don't need it for now. What we're interested in is just the distance from O to M. This movement, that's being made there from O to M. And it's just from there to there and there to there. So far, phi hasn't intervened. It's going to intervene later on in other calculations, but for now it hasn't, so we just leave it out. It's just from O to M prime, it's rho, suivant E rho, and from M prime to M is Z, the Z coordinate, suivant K. Is it clear?
All right, it's clear.
Okay. So the vector position, when we say vector position, that's how you define the position of any vector in this coordinate system. You use these things. So that's where now this comes from, this equation. OM is equal to OM prime plus MM prime, which is equal to rho E rho plus ZK, like I am from explaining. Rho E rho plus ZK. Rho suivant E rho plus Z suivant K. Rho in the direction of E rho plus Z in the direction of K. So when you tell someone this, now they will know. When you tell them, okay, so OM is going to be equal to in the direction of E rho. So the person knows, okay, E rho is oriented northeast, for example. Move rho steps. So the person will imagine now, okay, so I'll move rho steps in this direction, the northeast direction. Then you tell them from there now, move Z steps in the direction of K. So the person will know, okay, K is oriented upwards, like I'm going in the sky. So I'll move Z steps going up in the sky. So I'll move that and that. So the person now is going to know exactly where M is located in space. It's more explicative, it's more informative than just saying OM, just moving from O to M. the person won't know what you're talking about, even if you have seen it, but how exactly has the object moved in space? So you say, okay, it moved rho in the direction of rho, and then it moved up z in the direction of k. C'est clair?
Oui.
Okay, so that's the
Mr.
coordinate.
Charles,
Yes.
Mr. Charles,
Yes, yes.
okay, on the position vector there. So
Uh-huh.
now, is it important to like add an arrow there on the direction, or it's just the way it is?
You, on which direction, sorry? These top parts here, these lines are arrows.
Oh, yeah, okay.
Yeah,
I
they're
was
arrows.
trying to clarify on that point as well.
Yeah, they look like straight lines, but they're arrows. That's the printing error. As I mentioned, whenever you're speaking of vectors, always use arrows, always, always. If you leave out the arrow, your answer is going to be wrong, and professors take this thing serious. So now we come to this part here. I'm going to try and explain to you guys where all these are coming from. We are going to use trigonometry. As I mentioned to you guys last week, trigonometry is very, very important. So we are going to use it here to try and derive these formulas. And I want you guys to follow me very well. So what we're trying to do now is we're trying to make a relationship between the coordinate Cartesian and the coordinate cylindric, because sometimes in your calculations, you have to come out of one coordinate system and start calculating in another coordinate system. But how are you going to do that? Now, this is where you learn how you are going to do that. The correspondence, when we say rho is equal to what in the Cartesian system? When we say phi, how can we calculate phi in the Cartesian system? Z, what's Z in the Cartesian system? And vice versa. When we're in the Cartesian system, we have X. What's X equal to in the cylindric coordinate system? What's Y equal to in the cylindric system? And what's Z equal to in the cylindric system? This is the part we look at, or that. So we have established, or we have seen, that the vector position in the coordinate cylindric OM is equal to OM prime plus M prime M, which is equal to rho E rho plus ZK. So now, if I asked you, now write this in the Cartesian system for me. Imagine now you are calculating this in the cylindric system, or you are finding the vector position in the cylindric coordinate system, and I tell you, but I am working with the Cartesian system. Please tell me the coordinates in the Cartesian system. How are you going to transform this vector position, which is in the cylindric system with the rho and the rho, into the Cartesian system? So now we are going to do some calculations and we'll see exactly how. On peut lier les coordonnées cartésiennes aux coordonnées cylindriques like this. So we're trying to make this relation from rho phi z to x, y, z. So the formulas have already been derived. And that's what I'm telling you. Take advantage of this opportunity that I am explaining these things to you guys, and try and understand them, because the professors will not explain these things in details. They will suppose that you already know where they are coming from, or they will just not want to explain, because you won't be really working with these things exactly in the mechanics you'll be doing. So they will just skip these things. So take advantage of this opportunity. There are certain things that I didn't get in my first year or my first semester when I was doing this. I actually understood it on Monday when I was trying to go through, like the EFI part here, this part here. I just recently understood it. The owner of this polycopy even circled it also. They did not understand it because this is not my polycopy. So take advantage. I'm going to try and explain it to you guys. So they have given us here the formulas that have already been derived. As you can see, the formulas have already been derived. So they'll just be given to you like this. You can take them as they are and work with them, or you can be a good student, a good engineer, and ask yourself where they are coming from, how they were obtained, and how exactly to calculate them. So when you're moving from coordinate Cartesian to coordinate cylindric, in the coordinate Cartesian, you work with x, y, z. And in the coordinate cylindric, you work with a rho, you work with the angle phi, and you work with z. So x in the coordinate Cartesian is equal to rho cos phi in the coordinate cylindric. Y in the coordinate Cartesian is equal to rho sinus phi in the coordinate cylindric. And as I told you, the same Z we use in the coordinate Cartesian is the same Z we are using in the coordinate cylindric. So the Z does not change. So if I have, for example, I'm in the Cartesian system and I have OM equal to XE plus YG plus ZK, and I'm asked, hey, Charles, write that in the coordinate cylindric. I'll say XE, oh, XE, okay, I know X is equal to rho cosinus phi. So I'll write rho cosinus phi. And I know Y is equal to, oh, Y is equal to rho sinus phi. So where is Y, where is Y, I'll write rho sinus phi. And I know Z is equal to blah, 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 blah. So Z stays Z, so Z will remain Z as it is. Ainsi de suite. Now, where are these things coming from? So we come down here. We'll begin with this diagram. I tried to draw these things for you guys so that you can understand where they're coming from. If we look at this figure here, this figure there, it's the figure I tried to reproduce on the other diagram. It's not as perfect as this one because it was hand-drawn. I'm not so much of an artist myself, so you understand me. Just try to imagine that what's perpendicular is perpendicular, even if it's not showing in the figure. So this figure here is what I've tried to reproduce there. You have X, you have Y, and you have rho. This is what's going to interest us most because we want to find the expression for X in terms of phi and in terms of rho, and we want to find the expression for Y in terms of rho and phi. Z, not so much because Z is still the same in the Cartesian and in the cylindric plane. So we'll just work with the horizontal plane, this one there. So when we come down here, I tried to reproduce this. As I said, the figure is not perfect, but what we are interested in most is X, Y, rho, and phi. So we know that X and Y sont orthogonal. They are orthogonal to each other. They are at 90 degrees to each other. So the angle between X and Y there is 90 degrees. And as I explained on Thursday last week, try to work with right-angled triangles in everything that you do. In whatever you do, try to work with right-angled triangles. When you are trying to derive expressions, to derive formulas from such systems, coordinate systems like this, there's a lot of 90 degrees there. There's a lot of right-angled triangles you can form there. So try to look for them, find them, and use them to your advantage. As I mentioned, they are gold mines. They make your work very, very easy. So I want X in terms of rho and phi, and I want Y in terms of rho and phi, from Cartesian to cylindric. And I know that X and Y are at 90 degrees to each other. So with X and Y, I can actually form a right-angled triangle with a hypotenuse rho. If I project this Y here, I project it on this side. This dotted line I've drawn here, it's a projection of Y. I've projected Y on this side. Why have I projected Y? Because Y meets X at 90 degrees. So if I project Y this side, it will be meeting X at 90 degrees there. And I'll have my right-angled triangle there with X, Y, and the hypotenuse rho, with the angle between X and rho being phi there. So I'll extract this triangle here. It's more perfect than this one because this figure was not drawn to scale. It's not perfect. So I'll extract this triangle here I've formed, and I'll have that triangle there. So I'll have my X, which is this X, and I'll have my Y there, which is this Y, meeting at 90 degrees, which is this here to show 90 degrees. Then I'll have my hypotenuse rho, and I'll have my hypotenuse there here rho, with the angle between rho and X being phi, angle between rho and X being phi. I have my right angle triangle. From here now, c'est du gâteau. It's simple. I'll just begin. Cos phi, sokatoa. Cos phi is equal to the adjacent side of the angle phi, which is X, over the hypotenuse side, which is rho. I have this expression. Sokatoa, so sinus phi is equal to the opposite side, which is Y, over the hypotenuse side, which is rho. So sine phi is equal to Y over rho. What do I want? I want the coordinates in the Cartesian plane written in the form of the coordinates in the cylindric plane. So I'll be going from X, Y, Z to rho, phi, and Z. So Here, I'll just make x subject to the formula. So I'll say x is equal to this. So if I make x subject to the formula here, I'll be multiplying rho times cosinus phi. That means x is equal to rho cos phi, and y will be equal to rho sinus phi. As you can see from there, this is how they derive these formulas there. X is equal to rho cos phi, and y is equal to rho sinus phi. Just simply from this figure here, just project the y there, extract your right angle triangle, and from there just do a bit of trigonometry, so Katoa, the most basic trigonometry, and you get your formulas or your expressions there as that. Est-ce que c'est clair?
Oui, c'est clair.
Lovely, love. So from here, these ones here are now easy. So from here, we're moving from x from Cartesian to cylindric.
Excuse me, kindly explain how you project it again? Like, there's a point I'm missing out here.
All right. So I have this figure here is the same as this figure here, this figure there. Okay, this figure there. It's the same figure I try to reproduce on this page here. Then x, y, and z in this system, in the Cartesian coordinate system, x, y, and z are perpendicular to each other. So the angle between x and y is 90 degrees. And as I mentioned last week, I said that when you are trying to derive expressions, to derive formulas and all that in this manner, try to work by all means possible with right angled triangles, because right angled triangles are easier to work with. Very, very easy. The formulas for right angled triangles are already known. Either you're working with SOHCAHTOA or you're working with Pythagoras theorem, and all of them are known. You guys have been doing them for a long time now. You are used to them. The rest of the triangles will give you so much trouble because their expressions are complicated. So just try to look for right angled triangles wherever you can, form them, extract them, and work with them and get the expressions you are looking for. So I said from here, we are moving from Cartesian to cylindric, from Cartesian to cylindric. So we want x in form of rho, phi, or z, and we want y in form of rho, phi, z, and we want z in form of rho, phi, and z. But I said the z in the coordinate Cartesian is the same z in the coordinate cylindric. The z does not change. It's the same one. So the z, will just keep it as that. So in our calculations here, we are just going to be working with the horizontal plane, the x or y plane, because that's what we need. The z, we do not need it for now because z is the same in the Cartesian and in the cylindric coordinate systems. So we have the x, y there, and the rho being that. And we know that the angle between x and y is 90 degrees. And we want to form a right angle triangle. What we can simply do is we can project this y, get its parallel line, and project it there. So if we get this line and bring it there, it's going to come here. It's going to become this dotted line. I know these two lines are not parallel, but as I told you, the figures are not drawn to scale. Just imagine they are parallel. Yeah, so y and y, we project this y there. So when we project this y there, the angle between x and y is 90 degrees. So when we project this y there, the angle between them will still be 90 degrees. So we'll have the 90 degrees there, and we'll have a phi there, and we'll have x, y, and the hypotenuse as rho. So when we extract this triangle I have formed after projecting the y down this side, I'll have this triangle here with x and x there, y as y there, and the angle between x and y being 90 degrees. That's why I have this 90 degrees there, and the angle between rho and x is phi. The angle between rho and x is phi. Et nous voilà a triangle there that we can now work with using SOHCAHTOA. So if you just begin cos phi is going to be equal to the adjacent side over the hypotenuse side, which is x over rho. Sinus phi is going to be the opposite side over the hypotenuse side, which is going to be the opposite to phi is y over rho, which is y over rho. And here we want x in terms of rho phi z, and y in terms of rho phi z. So we just make x have like the formula. We will have x is equal to rho cosinus phi and y equal to rho sinus phi, as given by the formulas there. Is it clear?
Yes, it's clear.
Okay, good. So now this time we're going to do the opposite. Okay, we're going to do the opposite. We want a rho, phi, and z in terms of x, y, and z. Okay, a rho, phi, and z in terms of x, y, and z. So we have x equal to rho cos phi, and we have y equal to rho sinus phi. Now, from trigonometry, those of you that did additional mathematics, or those of you that have done trigonometry somewhere, sine squared plus cos squared is equal to
1.
is equal to 1, exactly. So sine squared plus cos squared is equal to 1. So if I add these two equations, the first two equations, I'll have x plus y is equal to rho cos phi plus rho sinus phi. Okay. Or before I add them, we'll begin by first squaring them. So we square both sides of this equation. We'll have x squared plus rho squared cos squared phi, and we square this one also. We'll have y squared is equal to rho squared plus sine squared phi. We just square these equations. We square the right hand side, the left hand side, right hand side, left hand side. When we square them, then after we square them, we add them. So when we add them, we'll have x squared plus y squared being equal to rho squared cos phi plus rho squared sinus squared of phi. Then from there, when we factorize a rho squared, it's going to be rho squared and between brackets cos squared phi plus sine squared phi. And as you've told me, you guys, cos squared phi plus rho squared, cos squared phi plus sine squared phi is equal to 1. So on this other side of the equation, I'll just have rho squared, because the cos squared phi and the sine squared phi will add up and give me a 1. So I'll have a rho squared equal to x squared plus y squared. What I want is a rho, not a rho squared. So I will introduce the square root. So when I introduce square root on both sides, it will become rho equal to x squared plus y squared le 2 racine carré. And that's where this comes from. Was that clear? I know it's hard when someone is just saying the calculations. It's better seeing them.
It's clear.
There I can repeat.
Yeah, please, you can just repeat.
Okay, so I began by asking you guys, cos squared phi plus sine squared phi is equal to
1.
It's equal to 1. And that's a formula you have to remember. If it's the first time you're hearing of it, know it and keep it in your heart. Such expressions simplify your work. You might meet a sine squared plus cos squared somewhere, just add them and get your 1 and continue calculating. You get rid of them. So cos squared phi plus sine squared phi is equal to 1. There. Then we want the expression of a rho in terms of x, y, and z. Okay. We want the expression of rho in terms of x, y, and z. So we'll work with these two expressions that we found here. We'll work with these two. And what I said was, we first begin by squaring both equations. So I square the left-hand side, I square the right-hand side. So I'll have x squared, and this side I square it, I'll have a rho squared plus cos squared phi. I square this one also, I'll have y squared is equal to rho squared plus sine squared phi. So I have squared both equations. Then after I square them, I'm going to add the two equations. That means I add what's on the left and I add what's on the right. So when I add what's on the left, I'll have x squared plus y squared being equal to what's on the right, which is rho squared cosinus squared phi plus a rho squared sinus squared phi. So when I reach that stage, what I'm going to do now is I'm going to factorize the rho squared, okay? Because I have rho squared cosinus squared phi and rho squared sinus squared phi. The rho is a common term there, so I can factor it out. So when I factor it out, I'll have x squared plus y squared is equal to rho squared between brackets cos squared phi plus sine squared phi. Now we have agreed that cos squared phi plus sine squared phi is equal to 1. So between brackets there I now have a 1. So I'll have x squared plus y squared being equal to rho squared times 1, which is just equal to rho squared. So up to this point, I have rho squared being equal to x squared plus y squared. When I square both sides of the equation, I'll have a rho, because I have squared, it was rho squared, I've square rooted it. Now I have the rho being equal to the square root of x squared plus y squared. That's where this comes from. Rho is equal to x squared plus y squared and square root, like that. Is it clear?
Yes, thank you.
Okay, lovely. I hope it's truly clear. Then we come to the angle phi. How are we going to get the expression for the angle phi? The angle phi again is also quite easy. What we just need is to have phi on one side and expressions on the other side. So the first time we added the first two equations here. This time around, we'll be dividing the two equations, okay? We know, okay, sine phi from trigonometry again. These identities, you guys should know them. That's why I'm asking you, so that you try to refresh your memory a bit, and then afterwards you can continue using them. So sine phi over cosinus phi is equal to what?
Tan.
Yes, sine phi over cos phi is equal to tan. If it's the first time you're hearing of it, take note. Sine phi over cos phi is equal to tan phi. That's that. So we are going to divide these two equations. What we are trying to do is to produce a tan somewhere, okay? So when we divide y by x, we divide the second equation by the first equation, we are going to have y over x is equal to rho sine phi over rho cos phi. Y over x is equal to rho sine phi over rho cos phi. Then the rho and the rho are going to cancel out because they are found in both the numerator and the denominator. So we are going to have y over x is equal to sine phi over cos phi. And you guys have told me with so much assurance that sine phi over cos phi is equal to tan phi. So the expression is going to become y over x is equal to tangent of phi. What's left here now is just to make phi the subject of the formula. That means the tan has to go to the other side of the equation. And when we take tan to the other side of the equation, we know it's going to become its inverse. On the calculator, you say tan minus 1 or tan inverse. But welcome to university, we denote it as arctan. I know it's the first time you are hearing of this. It was the first time when I heard of it when I came here. So perhaps some of you have heard it before. But arctan is just tan inverse, okay? I know you guys who did trigonometry in high school, you worked with tan inverse somewhere. You just write tan inverse, tan and the minus 1. But here we don't write tan inverse. We call it arctan. So when the tan goes to the other side, it's going to become arctan. So I'll have phi is equal to arctan of y over x. And that's your expression for phi. I'll go over that again. I know it's hard when someone is just telling you these calculations and you have to picture all of them in your mind. It's a bit hard to follow. So I'm going to repeat. I'll go over it slowly. I asked you, sine phi over cos phi is equal to, and you guys told me it's equal to tan phi. Well and good, it's true. Sine phi over cos phi is equal to tan phi. So when we were deriving the expression for rho, we added the first two equations. Now that we're looking for the expression for phi, we are going to divide them and not add them. So this time around, we will be dividing the second equation by the first equation. So when we divide the first equation over the first equation, we are going to have, on my left-hand side, we'll have y over x. Okay, when we divide the second equation by the first equation, on my left-hand side, I'll have y over x, or y divided by x. And on my right-hand side, I'll have rho sine phi over rho cos phi, or rho sine phi over rho cos phi. Now, the rho is a common term in both the numerator and the denominator, so we can simplify it. So the rho and the rho will cancel out. What I'll be left with now is y over x over, not over, but equal to y over x equal to sine phi over cos phi. Y over x equal to sine phi over cos phi. Now, sine phi over cos phi is equal to what? Tan phi. So on my right-hand side, the expression will become tangent of phi, tan phi, because sine phi over cos phi is equal to tan phi. So I'll have y over x is equal to tan phi. But what we want is the expression for phi in terms of y and x, not tan phi, but just phi. So I'll have to take the tangent onto the other side of the equation so that I just have phi on this other side of the equation. So when the tangent crosses the equation, or the cosine, sorry, when it crosses the cosine, goes to the other side of the equation, it becomes inverse of tan. You have tan on one side. When it goes to the other side, it becomes tan inverse. Okay, so we'll have phi is equal to tan inverse of y over x. But tan inverse is also called arctan, and we won't be working with tan inverse here in Morocco. We have never said tan inverse. We work with arctangent, arctan. So when it crosses the other side of the equation, it becomes arctan. So now our formula is going to become phi is equal to arctangent of y over x. Arctangent just simply being inverse of tan. Does arc have a specific name in this case? I don't get the question, Lawrence. What do you mean specific name?
Like something like a full name, perhaps.
No, it's just arctan. We just say arc sine, arc cos, and arctan.
Okay.
Yeah. So that's the expression there. Is it clear for the phi?
Yes.
Yeah, it's clear.
Okay, lovely. Then the z, as usual, the z remains z. Z remains z. Z does not change because the z in the Cartesian plane is the same as the z in the cylindrical coordinate system. So these are the expressions. Moving from Cartesian to cylindric and from cylindric to Cartesian, you use these expressions there that you have. You know where they're coming from. You've understood where they're coming from. You just now have to know them by heart and use them when you need to use them. Then we come to this, because we will not only be changing the x, y, z and the whole phi z, we'll also be changing the whole, the e phi and the z. We have to express it in terms of e, g, and k. The e, r, the e phi and the e z, the base vectors. As we said, z does not change, going from Cartesian to cylindric. So the ez is just the same, it's equal to k. In cylindric, we denote it as ez. In Cartesian, we denote it as k. They are equal, so they can be used interchangeably. So even in cylindric, you can denote it as k. You won't be making any mistake anywhere. Now we are going to look at where these expressions are coming from. And take note, these are vectors. These are vectors. They are vectors. You can see the arrows on their heads. They are vectors. Here, these were they were scalars. That's why we just worked directly with the trigonometry that we know and all that, because they were scalars. But here we will need to use some tools in vectors to calculate them. The e phi, oui, exactement. Then we're going to come back down here to see where they are coming from. We are going to use the same triangle we extracted, this one here, the right angle triangle. We are still going to work with this one, except this time around I have just flipped it. It's the same triangle, but it's just inversed, meaning the wire, instead of being down on the floor, it's now facing upwards. So heureux, you know, heureux is the vector in the direction of rho, okay? Heureux is the vector in the direction of rho. From this we see rho is this vector here in this direction there, and rho is the magnitude of the vector. But if we just get the vector rho, what do we know about rho? Rho, c'est un vecteur unitaire. So when we say vector unitaire, what do we mean? Its magnitude is equal to what? That's a question for you guys to answer.
1.
Its magnitude is equal to 1. So that means rho for rho, which is the magnitude of this line, is going to be equal to 1. Yes?
Yeah, I had network problem, so I didn't get what you said when you just started extracting the second one.
This one. Okay,
Yes.
I'm just beginning. I haven't really said anything that's going to lose you, so don't worry. You're still with us. Okay, so I was asking, say, vector unitaire means that the vector is, the magnitude of the vector is equal to 1, as you guys have told me. So for heureux, we know rho is the magnitude of this vector there. And this vector there is where heureux is found. That means for heureux, its magnitude being equal to 1 implies that rho in this case is equal to 1 as well, because rho is the magnitude of the vector found here. Or rho is the magnitude of the vector found here. And heureux is also found there, being the vector unitaire for this vector found there. That means rho is equal to 1. Heureux, that's ending somewhere there with a rho equal to 1. And that's what I tried to say here. For heureux, it's unitaire. Heureux is a vector unitaire. That implies that rho is equal to 1 in this case. Just in the case of a vector unitaire, the rho will be equal to 1. The magnitude of that vector, which is rho in this case, is going to be equal to 1. So if rho is equal to 1, the x that we had calculated here as being equal to rho cosinus phi, because rho is equal to 1, is going to become cosinus phi. So that's going to be x is equal to cos phi. And y is going to be equal to, because rho is equal to 1, it's just going to be sinus phi. That means this, the x there is going to be cos phi, and the y is going to be sin phi. Simply, if rho is different from 1, it's going to be rho cos phi, rho sin phi. But because rho is equal to 1, heureux being a vector unitaire, the expression becomes x is equal to cosinus phi, and the other expression becomes y is equal to sinus phi, and that's that. So when we come down here, we come down there like that on this triangle, we have heureux there. Normally it doesn't go in this direction, it goes in that direction, but we are just trying to do some calculations, so it's just like that. It's not changing anything. So heureux, like that. So we are going from there to there, and from there to there, from there to there, and from there to there, for us to move in the direction of heureux, or for us to move from 0 to heureux is this way and that way. So we are moving x, e plus y, g. X, e plus y, g. Okay, now x is equal to what? X, we've said, is equal to cosinus phi. So we'll have cosinus phi, e, and y. Y is equal to what? Y is sin phi. So it's going to be sinus phi suivant g. So heureux being a vector is going to be moving sin cosinus phi suivant e, or cosinus phi in the direction of e, and sinus of phi in the direction of g. That's going to be heureux, and that's why we have heureux being equal to cosinus phi suivant e plus sinus of phi suivant g, like this one here. That's what heureux is equal to in the coordinate Cartesian. It's cos phi e plus sinus phi g. And that's the expression they have here, this one here, heureux being equal to that. Cosinus phi e plus sinus phi g. Was that clear, or should I go through it again?
Kindly repeat.
Okay. I'm going to repeat. So we have heureux. Heureux is the vector there. It's there. It's in the same direction, not in the same direction as rho, but heureux is what determines the direction of rho. Okay, and we know that the rho is the magnitude of the vector found there, or the vector suivant heureux. The vector that follows heureux, its magnitude is equal to rho in the coordinate cylindric. Okay, so in this case, the vector we are dealing with is heureux itself. Okay, heureux itself. And we know heureux, c'est un vecteur unitaire. It's a unit vector. And for a unit vector, we know that a unit vector is a vector with magnitude equal to 1. So if rho is the magnitude of the vector in this direction, that means its magnitude or its value is going to be equal to 1 in the case of rho, because E rho has a magnitude equal to 1. And the rho being the magnitude is going to be equal to 1. But only in the case of E rho, its vector unitaire is a rho being equal to 1. That's why I said here rho for E rho, because E rho is a unit vector. So the vector unitaire, it implies that its magnitude, which is equal to rho, is equal to 1. Okay, and we had already found the expression, these expressions here, x being equal to rho cos phi, y being equal to rho sinus phi. And in the case of E rho, in the particular case of E rho, where rho is equal to 1, this rho here will be 1, and this rho there will be 1. So the x will become cosinus phi, and the y is going to become sinus of phi, two simplement, x cos phi and y equal to sinus of phi, because the rho is equal to 1. So here where I have x here, this line here is equal to x, it will be cos phi. And this line here that's equal to y is going to be sinus phi. But only for E rho. For E rho, that's it. So E rho here I've drawn now. This is just a triangle. I'm just writing the values, but now I'm dealing with vectors here now. I'm dealing with vectors. So that's why I have this vector here, E rho. This vector, E rho. So for us to move from this point here, 0, up to E rho, if you look at this figure here, we are moving x and then y. We are moving x and then y. That's why I got this triangle. We'll be moving x, then y. X, then y, for us to reach at E rho. But we have found the expression for x to be equal to cosinus phi. So here where there's x, I can just write cosinus phi. And here where there's y, I can just write sinus over phi. And this is going to continue until you finish your mechanic studies. You do mécanique des solides, mécanique du point. Whenever you're dealing with unit vectors, whatsoever, if you are trying to derive them in the xy plane, x will always be cos phi and y will always be sinus phi. That's that. Sometimes we just look x cos phi, y sin phi. You write and you continue calculating. But for you guys, you are beginners, so don't try to use such shortcuts. You might end up misusing it and getting the wrong answer. Just follow the procedure, the way things are supposed to be done. Then when you reach cos phi and sin phi, you advance. But after you have practiced a lot, you will now stop deriving them. You just know for vector unitaire, I know x is equal to cosinus phi and y is equal to sinus of phi. So x there is cos phi and y is sinus of phi. So for me to move from 0 to E rho, I'll be moving up the x-axis first of all, and I know x, I'll be moving cos phi suivant I. So E rho will be equal to cos phi suivant I, like that. And then I'll go in this direction now to reach at E rho, and I'll be moving y steps, and y is equal to sinus of phi suivant J. So finally, the expression is going to be E rho equal to cos phi I plus sinus phi J. Is it clear?
It's clear.
Okay, love. I see it's 11:10. I'll just quickly go through E phi. We'll end there. Then tomorrow we'll pick it up from the spheric coordinate system. Yeah. So E rho. Now, as I told you, take advantage of this moment that I'm explaining these things to you. If possible, note them and go through them, understand them, because your professors won't explain these things to you. Now, as we mentioned earlier on, E rho and E phi are perpendicular to each other. They are found in the same plane, the horizontal plane, and they are perpendicular to each other, E rho and E phi. And as I told you, it's hard for you to see the orientation of E phi. It's tricky to imagine it. For E rho, you know that it's between the x and y there. Okay, you know it's between the x and y because of this rho showing us where it is. But for E phi, it's a bit hard to imagine because all you know is just perpendicular to the two of them. But perpendicular in which direction? It's hard to imagine a bit. So it's hard to understand exactly where its expression is coming from. So I tried to figure out something here that can show you guys exactly where it's coming from. So we know that the E rho is between x and y. So I have my x there. It's not showing here, but this is x. I have my x there, and I have my y there. Okay, and I have my angle between x and E rho being equal to phi, from this here, the angle between x and heureux or he is equal to phi. So I have this angle there is showing me that the angle between heureux and x is phi. And if the angle between heureux and x is equal to phi, that means the angle between rho and y is going to be equal to, because x and y are at 90 degrees to each other, meaning this angle here, total angle from x to y is 90 degrees. And this, if this angle just up to there is phi, that means this other angle here will be 90 minus phi. Okay, I'm sure that's clear. So pi over 2, this is in radians, pi over 2 is equal to 90. So this angle here is pi over 2 minus phi. Now, I know that heureux and phi are perpendicular to each other in the horizontal plane. So I can try to project phi, just making sure it's perpendicular to heureux. So if heureux is this vector here, I can draw a vector there representing phi. Just ensure that this is 90 degrees here. The angle between them is 90 degrees. So if the angle between them is 90 degrees, and this angle here is pi over 2 minus phi, this angle here will be equal to phi. So that when I add these two angles, they should give me 90 degrees. When I add pi over 2 minus phi plus phi, the minus phi and the plus phi will cancel out, and I'll remain with pi over 2, which is 90. So these are angles. I'm sure you've all done angles before. So you're just trying to calculate the angles. It's just clear, ça se voit. So if this is pi over 2 minus phi, this angle here between y and phi is going to be equal to phi. And the angle this side between phi and minus x, why is the x minus? Because on my figure, x is oriented upwards. So if I start going down, it's going to become minus x because I'm going in its opposite direction. As I told you, vector, if a vector is going to the right, and I draw a vector that's parallel to it but going to the left, it's going to be its opposite. They are equal, but if they are of the same length, they will be equal, but they will just be opposite to each other. So I wrote minus x there to show you that it's in the opposite direction of our conventional x, the x we are using in this case. So the angle between minus x and phi is going to be pi over 2 minus phi again. And because this is a straight line, all these angles here, when you add them, they'll give you 180 degrees or pi. I'm sure you guys remember all these things. So we are trying to derive the expression for phi. So what's going to interest us is just this part here, the down part here, y minus x. So I can project this y down here. As we said, parallel vectors are equal, provided that they are in the same direction. And if they're in the opposite direction, they are just opposite. So you just add a negative sign. So I project this y down here. If I project it down there, I'll form this triangle here. And I know y and x are meeting at 90 degrees. So if I project this y, I'll form this triangle there with a 90 degrees here, a 90 degrees angle there, and I'll have a right angle triangle, alhamdulillah. And the calculations from there are going to be very, very simple, as we have seen. So I'll have this right angle triangle with a 90 degrees there. And as I told you, when you are dealing with vector unitaire, x, sorry, just a minute. We will need to find the expressions for these things. Okay, we need to find the expression for these calculations. Sorry, for these lines here, the dimensions there, the x and the y. They are not the same as what you had there. They are going to change a bit because the angle has changed in this case. That's why I said for you guys, because you are just starting, don't take it directly as x is equal to cos phi and y is equal to sin phi. You might end up confusing yourself for getting the wrong figures, because here now it's changed. The x won't be cosinus and the y won't be sinus because the position of the angle has changed. So as I said, if I project this y down here, I'll have this z. Here. And I'm sure you guys remember the z property, that the angle there is going to be equal to the angle there. If you don't remember the z property, just draw a line there, the y, form a right angle triangle, then you have a pi, you have a pi over 2 there in 90 degrees, and then you have a pi over 2 minus phi there. Then when you add all the angles inside the triangle, they give you 180, or they give you pi. So when you add pi plus pi over 2 moins phi, it should plus x, the angle we're looking for there, it should give you 180 degrees, or pi. When you solve, you'll find that the angle there is going to be phi, which is the angle we want. So in this triangle here, our phi is here. Our phi is there. So that's our phi in this case. That means the opposite to this phi is going to be this line here. That's going to be the opposite, which is sine. And the adjacent to this angle there is going to be the y here, which is cos, So this is going to be sine, and this is going to be cos, because the angle this time is here. In this triangle on top, the angle was there. That's why we had the cos on the x and a sine on the y. But this time the angle has changed. It's found here. So we'll have a sine on the x because it's the opposite side, and we'll have a cos on the y because it is the adjacent side. So I'll have sine and cos. So for me to move down E phi, this is going to be E phi. The line there is E phi. So from E phi, I'm moving from 0 to E phi. I'll move like that, and then like that. I'll move like that, and then like that. And we know this is sine. So this is going to be sine. But we're not following I because I is going up. This time we're coming down. So we'll be following minus I. So it's going to be minus sine I being equal to cos. The g in this case hasn't changed direction. It's still the same direction as there. It's going to be plus cosinus phi of g. And that's where this comes from. E phi is going to be equal to minus sine of phi E plus cosinus phi g. Is that clear for E phi? And that's going to be your expression for E phi, minus sinus of phi I plus cosinus of phi g.
You can just repeat what you're saying.
Okay, I'm going to go over it one more time. So we know that E re and E phi are at 90 degrees to each other, n'est-ce pas? That we know. They are at 90 degrees to each other. So if I have my E rho there between x and y, I can draw, or I can project a vector perpendicular or at 90 degrees to E rho, and it's going to be my E phi, still in the horizontal plane, because E rho and E phi are together in the horizontal plane. So if I draw a vector perpendicular or at 90 degrees to E rho, like that, I can make this my E phi, because E phi is perpendicular to E rho, base for a base. They are autonome, that means they are normé equal to 1, and they are orthogonal at 90 degrees. That's why I have projected this E phi at 90 degrees to E rho like that. And then we were working with this figure here, the figure we're working with at the beginning was this one, when we were deriving E rho. And we saw that the angle between x and E rho was phi. So that means the angle here between E rho and x is going to be phi still. It's phi. And then we know x and y are also perpendicular to each other. That means the angle here from x to y is 90 degrees. And if the angle from x to y is 90 degrees, and from x to E rho we have a phi, that means the angle between E rho and y will be equal to 90 minus this phi. So that it gives me pi over 2 minus phi. So that when I add these two angles, they should give me a 90 degrees, because x and y are perpendicular to each other. They have 90 degrees between them. C'est ça. Alors, c'est pi sur 2 moins phi. Then we have said that E rho and E phi are also perpendicular to each other. The angle between them is 90 degrees. So if E rho and E phi are perpendicular to each other, and this angle there is pi over 2 minus phi, that means this angle here is going to be phi. So that when I add them, they should give me pi over 2 or 90 degrees, which is there. So this angle here between y and E phi becomes phi. Y and E phi, the angle between them is phi. And then If the angle between these two is phi, it implies that this angle here is pi over 2 minus phi. I don't think I need to explain this. You know it. The angle between x and y is 90 degrees. So that means this angle here will be 90, the total, minus this angle there. So it's pi over 2 minus phi. Why is this x negative? Okay, I'll explain. It's because we are going in the opposite direction of our conventional x. The x that we have here is going upwards, or it's oriented vers le ciel, le sky. But our x here is oriented vers le bas ou le sol, the ground. So we will have minus x because it's in the opposite direction. That's why I have a minus x. I told you parallel vectors are equal if they are of equal magnitude, but if they are parallel but in the opposite directions, you change the sign. It becomes minus x, minus y, minus z, minus whatsoever vector you are dealing with. If they are equal in length but opposite in terms of their direction. So because we are dealing with earthy this time around, we want the expression for earthy in terms of I and j in the Cartesian plane. We are going to work with this triangle, this plane down here, the minus xy. Minus xy is the plane we are going to be working with because we want the expression for earthy. So as I said, and as I have mentioned countless times, work with right angle triangles, work with right angle triangles, toujours work with right angle triangles. So I can get this y and I can project it down here. Or if you don't want to project the y, you can project the x, you can bring it this side. Ça sera la même chose, okay? But for some reason I projected the y, so you can project the y if you want. So I project the y, I bring it down here. It's going to be like that. And because the angle between x and y is 90 degrees, I'll have a 90 degrees angle there in this right angle triangle I'm going to form, which I have extracted there. Okay, so I'll have a 90 degrees there, and I'll have a pi over 2 minus phi there. That means I'll have my phi there. When you just work out the angles in this triangle there, you'll find that phi is here. So when I have my phi there, I can now easily calculate them. I already explained why x is equal to cos phi and why y is equal to sin phi in this figure. The same principle is going to apply there. So that means I just have to look for the opposite of the angle, the angle being there. Its opposite is there. So from SOHCAHTOA, I'm going to have a sin phi here, and the adjacent is there. So from SOHCAHTOA, I'll have a cos there because adjacent, the angle is here, it's found there. So I'll have cos and I'll have sine. The reason why they have changed is because the angle has changed. In this figure, we had the angle there. And because the angle was there, x in this case was the adjacent side, so it was cos, and y was the opposite side, so it's a sine. But in this case, the angle is there, so x has become it's become the opposite side, so it's become the sine, and y has become the adjacent side, so it's the cos. Okay, so now that I know that this dimension this side, or this line this side, is equal to sin phi, and I know that this one this side is equal to cos phi, il me reste maintenant de montrer, to show just how I am moving from point 0 to the vector phi. I am moving like this to that point, from this point to that point. Okay, so from there to there, if I want to give something more explicative, I'll be moving like that and then like that, or like this and then like that. But we'll work with this and that. So we'll be going down x, then y. Not down x, but down minus x, because it's in the opposite direction. And I know x is equal to sinus of phi. So I'll have minus sine phi I plus this one here is cos phi, because y is equal to cos phi in this case from these calculations there. So I'll have cos phi suivant j. So for total, the vector phi will be equal to minus sine phi suivant I plus cosinus of phi suivant j, which is this expression there, which was also found there. The same thing, minus sinus of phi I plus cosinus of phi j. It might not be so clear now that I'm explaining them to you, but afterwards, when you have some time, perhaps in the night, or I don't know when, just get a piece of pen and paper and try to derive these things yourself. Try to form these expressions, see where it's not clear, ask your friends if they understood. If none of you understood, then you can come to me and I'll explain these things to you. Just try to understand where they're coming from now, and then try them again. Try them and try them and try them and try them and try them, and you'll find that they are actually very easy. And you have to learn how to do these things, these techniques, the cos phi, sin phi, the SOHCAHTOA, the trigonometry there and there, the right angle triangles. These are the things you'll be working with a lot in mechanics. Mécanique du point, mécanique de solide, when you reach it, these are the things you'll mostly be working with. So you have to be really good at doing them, at identifying right angle triangles, at working out angles on a plane or angles in a triangle, and also at finding these expressions, at finding movements of vectors and all that. I don't know if that was clear, the explanation I gave.
Clear.
Just give us some work to try out. Okay, I'll give you work when we finish this whole topic. Then we'll do some exercises. In those exercises, you'll be doing the same thing. So don't worry, I'll give you the work. The work is going to come. Let's just finish this first part, then we can do some questions on them. Then the last part, just 2 minutes, is a cas particular of the coordinate cylindric. So when you have coordinate cylindric, normally we had rho, phi, and z. We had the horizontal plane, which was re, phi, and the vertical plane, which was k. But sometimes the object you are studying might not be making that translation I told you about up and down the z-axis. All it might be doing is just rotating around the z-axis. It's just rotating around that. It's not moving up and down. Like when you put a satellite around the Earth and it's just rotating around the Earth, just rotating. It's not making any up and down movements or any of that sort. It's just rotating around. There, in that case, the Z becomes 0. And in that case, we are working with a coordinate polaire. We call it coordinate polaire because the Z is equal to 0. There's no vertical axis. You only have the horizontal axis. And the only movement it's making is a rotation around the z-axis or the point or there, and that's what we call the coordinate polaire. And these are the workings or the calculations from the coordinate polaire. Here we had x, y, z, we had x, y, z, we had whole phi z, x, y, z. In this case, we have no z, because z is equal to 0. And that's the only difference between the coordinate cylindric and the coordinate polaire. It's that in the coordinate polaire, z is equal to 0. It's 0 because there's no translation up and down the z-axis. And that's the last part of our discussion today. If there are no questions, we'll be ending here. Are there any questions?
I've got a question on for those equation.
Sorry, there's a noise in your background. I don't know what's causing it. I don't know if you're moving or what, but I can't hear what you're saying.
Saying that on the part where you're explaining those equations, questions.
Uh-huh.
Yeah, like last part here where you're explaining.
Yeah.
I don't understand how the direction of how it changed. Because in the first part, the direction of the if was facing the other side.
Oh, yeah. Okay. So you mean here the Earthy is going like that and the is going like that?
Yeah.
Yeah. So as I told you, the figure I was just drawing there. It's just the way it's appearing, but the meaning is not changing. The essence or their values are not changing in any way. You see, for the here it's facing, it's looking like it's going down, okay? And in this case, the is going that way. It's going that way because my x and my y are in this direction. If I change my x and my, you've seen my x and y here. X and y are like this. It's like they're facing down, and that's why the was in this direction. But when I drew this figure, my x and y, it's now like they're oriented upwards. That means the will be oriented upwards with them also. The value has not changed. Nothing has changed. Everything is just the same. It's just that the orientation of my vectors, I have just changed it a bit, but they are all still the same. They are relations with each other. What's important here is their relations with each other, the angles they are forming with each other, and their values, they still remain the same, even though I have changed their orientations, but they are still the same. Because here, what's important is not the orientation, but it's just their relations with each other and their values, because we are just trying to derive their expressions, their values, a two, not their orientation. That's not really important at this point. That's why I drew it like this, the x, y, and the heureux between them. And that's how it is even on this figure, x, y, and heureux between them, with an angle phi between x and rho, with an angle phi between rho and x. And because the heureux has now changed, this direction is going this way, the phi is now also going to be that way, that way. That's because that's how it is with relation to heureux. That's how it's meeting heureux at 90 degrees to heureux in the horizontal plane. The orientation here is not so important because I'm just trying to derive its expressions. That's why I have drawn them like this. But if the orientation was important, I would have drawn them in the same sense you are seeing them there, with x and y facing downwards and the rho oriented downwards and the phi oriented upwards. But it's a good remark. It's a very good remark. You get the explanation.
Yeah, I get it.
Okay. Lovely. It's just because the
I also
orientation
have
here
a
is not so
question.
important. Uh-huh.
Yes, can you scroll up a bit on that big diagram?
Yeah.
Yes, yes. Here, you have written EX.
Oh no, it's Ika. Sorry, my handwriting. It's not looking clear. It's Ika.
Then it's parallel to
Z.
Z.
Yes. Eka is the same as Z. As I told you before, Eka is a vector unitaire for Z. We've just projected it this side so that we have all of them at the point M.
Okay.
Yeah. Any other questions? Feel free to ask where are not clear. Okay, no questions. Silence is taken as no questions.
One question. So is it always that EP and the theta always be perpendicular to each other?
Yes, when they are a bars that's autonomy, a bars autonomy, they'll always be perpendicular to each other. And when mostly in your exams, when the question begins, they will tell you soit heureux, phi, ek, une base autonome directe. They'll tell you that autonomy. When they tell you une base autonome, then you know all the axes of that base, the heureux, the phi, and the ek, they are all perpendicular to each other. Excuse me.
So I have a question. Another question. On this same diagram, from the extraction of this triangle which you came up with, the one showing phi, theta, y there, x there, then I think you extracted it from this original one, right?
Yes, we extracted it from this part here, this triangle here.
Yes. Then why did you write Z down here?
The Z. Where's Z?
The one, I think it was supposed to be X.
Ah, you mean this one here?
Yes, yes.
Ah, no, this is X. So sorry. Oh, my handwriting is. Je m'excuse. This is X. I was just fast when I was writing these things, but this is X. The Z is here. This is Z. This one is X. It's all.
Thanks.
All right, all right. You're welcome. Any other questions, ladies and gentlemen?
No.
Okay. Sorry for taking too long, and I'm sorry about the disruption that happened earlier on. We've taken too long. We've gone over the time. excuse myself again, but I'm going to have to release you now because you have class at 12. All right, good day to you guys. On se verra demain, inshallah, at 12 hours. Sorry, I think we'll do it in the morning again at 9. I'll talk to the person with the session in the morning.
Have a good day too.
All right.
Good day.
All right, guys.